Hi there, my name is Christopher Wurst and welcome to the first video on Homework 6, the final homework for material energy balance. This one's looking at vapor-liquid equilibrium. So the question for this video is part 1. It asks us to derive the expressions that can be solved for the due temperature, due pressure, bubble temperature, and bubble pressure for an ideal mixture of n components that follows Raoult's law. We're going to do bubble pressure, we're going to do this in the opposite direction, bubble pressure, then bubble temperature, then due pressure and due temperature. So we can start writing it out. Now, it asks us for Raoult's law. So I'm going to draw that first. Here. Double check that you can see. Okay. So first and foremost, the question's referring to Raoult's law. Which states that the Raoult's law, if you can see that, I'll draw that figure. There, now you can see that. So Raoult's law states that the mole fraction of the component I, that can be any component, of component I in the liquid phase multiplied by the saturation pressure of the component in the vapor phase is equal to Yi, which is the mole fraction of the component in the vapor phase multiplied by P, the total pressure. So with that, I'm going to draw out the situation that we're looking at. So we're first going to look at the bubble point. So the bubble point is when in a container of all liquid, it is the pressure and temperature that the first bubble of vapor forms. Now in a pure component, that's simply the boiling point, but in a 2, 3, however many component mixture, in this case an n component mixture, it means that it is then at that pressure and temperature that the bubble first starts, or first forms. So let's start with the bubble pressure. So I'll scoot over to this side. So bubble pressure. So if we know that Pi, the pressure the vapor pressure of a certain, or the pressure of a certain component is equal to Xi, that mole fraction in the vapor phase, multiplied by the saturation vapor pressure. So this is moving to here. This is equal to Pi. Well, then we know that the total pressure is equal to the sum of all of the pressures in the vapor phase, or all of the pressures. So P1 plus P2 plus P3 plus ... however many components you have until you have Pn. In a binary, you would only have pressure 1 and pressure 2, and etc., etc. So that means that if you have this here and you substitute this in, you could also say that pressure is equal to the sum of Pi, where I is equal to 1 to n, which means that it is also equal to the sum from I is equal to 1 to n of the mole fraction of the liquid component in vapor phase, multiplied by the vapor saturation vapor pressure. Now, this is not immediately important, but it will be important in future parts. What happens to Yi here? Well, Yi, which is of course the mole fraction of the liquid phase, is equal to the mole fraction in the vapor phase multiplied by, mole fraction in the liquid phase multiplied by the saturation vapor pressure divided by the total pressure. So that means if we factor this in here, that means that the mole fraction in the vapor phase, I've been getting those two mixed up, X is for liquid, Y is for vapor, is equal to the pressure of one component divided by the total pressure, or is equal to, if we change that to the total, which is of course equal to this, the sum of all the separate pressures, and if we change them to their liquid mole fraction multiplied by saturation pressure, we get that the liquid mole fraction multiplied by the saturation pressure of a single component divided by the sum of all of the liquid mole fractions multiplied by the saturation vapor pressures of all of the components, that sum there, is equal to the vapor, that vapor mole fraction of the individual component. That's not immediately important, but it will be important later for graphing and for calculations. So I'm just going to transcribe this here. So we can move on to bubble temperature. And remember, this is the sum from I equals 1 to n, so if we don't know how many different components we have, we can modify it however we like. So I'll erase this. And now we're going to move on to bubble temperature. Now, bubble temperature is interesting because, like many of the temperatures that we were trying to find in previous homeworks, it's buried in one of the variables. So this vapor pressure and saturation, we'll be using it in the coding in part 2. Specifically, we're going to be using the root function to modify the temperature to really find the temperature, but all that we need to know in this case is that the saturation pressure here, that saturation pressure there is where the temperature is. So if the bubble pressure is equal to the sum of the liquid mole fraction multiplied by the saturation vapor pressure, and that is for every single component, if we modify, all we have to do is to add them all up, and then eventually, of course, we're going to be using that, the equation, the properties equation that you've seen before in homeworks, but since we can just write it out, we know that the log 10 of the saturation vapor pressure is equal to A plus B over C plus T, and now we have found our temperature here. So what we're basically going to be doing is adding this all up and then modifying this temperature so that this is equal to our guess, or what we want, our bubble pressure. A little complicated, but it'll make sense once we actually graph it out and get the temperature. But all that we need right now is that we have the temperature here in this equation. It's present. So I'm just going to write this one so it'll combine with, this equation so it'll combine with the bubble pressure. Okay. So now we have bubble pressure and temperature. Now what? What's next? Well, they want the due temperature and pressure, so we're going to do that. I'm going to first erase. I'm going to erase this. Now, due point is a different thing. It's a different situation. Instead of all liquid, the only thing that changed is that in our little drawing, the only thing that is in the container is vapor. Now, the dew point, like the bubble point, is when the first drop of liquid forms. You would call that the condensation point or something like that in a pure liquid, but in a component, it's the dew point because it varies. So, let's begin on finding that out. Now, I'll write dew over here. Dew pressure, and I'll still do the equations here. So, now for a little bit of a common sense that is a little hidden. It's common sense, but it's not so common sense. We know that mole fractions, they're effectively percentages. They must add up to 1. So the mole fraction of that in the liquid phase must be equal to 1. Okay, that's interesting. Now, what does that mean? Or how do we use that? Well, if we have xi here, the liquid phase mole fraction, I'm going to write that out. Let me rewrite Raoult's law. And we're looking for this pressure here. And remember, if we're looking for key idea, if we're looking for the pressure, the temperature is constant. If we're looking for the temperature, the pressure is constant. Now, of course, we know that both of them are constant because they are related to each other. For any one pressure, you have one temperature that makes the point, but it's an important thing to remember. But what that means is that if we divide over and we have the mole fraction in the liquid phase is equal to the mole fraction in the vapor phase multiplied by the pressure divided by the saturation vapor pressure, we know that the sum of that from I equals 1 to n, and we know that this is equal to 1 is equal to the sum from I equals 1 to n, however many we have, of the vapor phase mole fraction multiplied by the pressure divided by the saturation vapor pressure. We can then take this pressure out, and I'll write it down here, goes to 1 equals P, the pressure, multiplied by the sum of the quotient of the vapor pressure mole fraction, the vapor mole fraction divided by the saturation pressure. That means that the pressure is equal to 1 over the sum of the vapor phase mole fraction and the saturation pressure. So we have that, and we're done with that. We can use that to find our pressure. So we have that equation done. And I'll write it underneath. Now, let me erase this. Now, like bubble pressure, bubble temperature, dew temperature is going to be, again, the root function and graphing, or not graphing, but calculations to find it on the computer, but it effectively follows the same idea. So that means that really, with this, all that we're going to be doing is doing the same thing. So we have our temperature here. So all we're going to be doing is putting effectively the sum of this equal to the total pressure for the dew pressure, and then finding the root, much like on bubble temperature. It's just the dew pressure equation is slightly different. So with that, on the left we have bubble, and on the right we have dew. I think that's, yes, okay. That means that we have found the equations that we're going to be using. Now, we're going to be using them for both equations and graphing, and I'll explain the graphing in just a minute in part 2.